So the three laws of motion by Newton are the most important laws in physics. So let's review the laws. So the first law says, well, an object at rest will stay at rest, an object in motion will stay in motion. And that is only when there's no net force on it. So we can say that its acceleration is equal to 0 if net force is equal to 0. This net force is defined as the sum of all forces, or simply a list of forces. Let's put some vector signs here. F1 plus F2 plus F3, etc. So we add all the forces vectors together, and we have 0. They all cancel each other, and then there won't be any acceleration. So this concludes that the velocity will be a constant. Let's put vector signs on all of these. Velocity being constant means it has a constant magnitude and also has a constant direction, so it doesn't change direction. And if you recall uniform circular motion, the velocity does have a constant magnitude, but the direction keeps changing, so that is not this situation. Okay, so the second law says, well, what if there is a net force? Then the net force is related to the acceleration. So force net is mass times acceleration. So it relates the force with acceleration, and the mass is this factor that determines how much acceleration is going to be observed for a certain force applied to it. So you can write it this way: acceleration is 1 over mass times force net. This is easier to understand. You have a force, and depending on how much mass you have this response from the object by accelerating. So the more mass, the same force, the less acceleration. And this is a generic case for the special case of the first law. The first law is just when A is equal to 0, F net is equal to 0. And this Newton's second law, we usually just say N2L. This Newton's second law is the most important one of the three laws, because there's an equation, and you can use an equation to solve problems. Okay. And the third law says something about force of action and reaction. So force of action and reaction. Say if you have two objects, A and B. So force on A, this looks like an N, acted by B. So this is force on A, acted by B, and this is force on B acted by A, and they're actually equal and opposite. So if A pushes B with a force X amount newtons in a direction, then B also pushes A with that same amount in the opposite direction. So these are called action and reaction pairs. And there's no need to say which one's the action, which one's the reaction. Although we usually say, well, somebody pushed you, they acted on you, and you reacted by basically pushing back. But that's irrelevant here. The action reaction is just a way to call the two forces. So the way that this formula can be used is sometimes we need a force, such as forces between objects, say objects that are stacked together against each other, a stack of two boxes. So say there's a box here, there's a box here. So if this is top box is A, bottom box is B, then A feels B pushing up, supporting A. So this is the force on A by B, right? And B also feels A pushing down. B does not feel A's gravity, although it's reasonable to say that A pushes as much on B as much as gravity pulls on A. B never feels A's gravity. B doesn't have A's mass. B does feel A because A pushes down on B. So B by A. They're equal and opposite. So when you have objects that are in contact with each other and you need to analyze both objects' motions, this is when you use forces of action and reaction. But when you just have one object, say sitting on an inclined plane or maybe sitting on a level surface, something like this, you don't have to include this. You know that the surface is pushing this object A. This is A, this is surface. So this is, you can just call it normal, or this normal force from surface. You know that A also pushes down on the surface. This is surface felt by A's push. This is A feeling the surface pushing upward. Right, so these are equal and opposite, but this force is not useful because this force acts on the surface, or maybe it's a table. And if the table isn't really part of the motion, the table is completely stationary, then the force on the table does not have anywhere to go on the equation. So we usually just ignore that. We just only look at objects that are that we're interested in, such as the stack of two boxes. And there's also surface forces, B pushing down on the surface pushing up on the B, but we only consider the surface pushing up on the B because B pushing the surface is acting on the surface. So that's the surface here, which is considered stationary, so we don't really need that force there, right? So these are the three laws, and we routinely use them in diagrams like these ones to analyze forces before we can use that formula to solve problems. So what are the forces we're interested in looking at in this chapter is we have, okay, let's see, forces. We could have gravity. So it could be Fg, or it could be equal to W, different symbols, and this is equal to mg. And the direction is downward, and magnitude is a constant m times g. So this is one force. Another force is normal force. A normal force is either Fn, or you can use an n for it. And this one doesn't have a magnitude predetermined. So this is depending on situation. Okay. And what about direction? Away from surface. Or surfaces, because one surface cannot push, right? There has to be two surfaces. So I'll give you some examples. Here is a simple example where you have one object sitting on surface. So the surface pushes up with this force, right? Away from the surfaces, there's the support surface and the bottom surface of the box, right? Away from the surfaces, right? And there's say the same box sits on an inclined plane. Away from the surface is not vertical anymore, right? Away from the surface is this. So this away is actually perpendicular. Right, so we can put a right angle here. So the normal force is not necessarily a force that's vertically up somehow against gravity. It depends on which direction the surfaces are being pushed. You can even have this very extreme situation here. Say I'm erasing a whiteboard, so this is my eraser. I need to push my eraser against the whiteboard so that it doesn't fall. So when I push, the surfaces will be pushed against each other, and this surface wants to push back. This is the whiteboard pushing back. So the normal force could be in any direction. Now you see that could be even in the downward direction if I push something against the ceiling, right? So this really depends on the orientation of the surfaces, and the direction that is always right is perpendicular to the surfaces in question. Okay, so that's a normal force. We also have tension. So tension will be Ft or T. And magnitude also is unknown, is dependent on situation. And direction. So tension tends to pull, say there's a string or rope. Tension tends to pull the ends of the string or rope towards each other so that the rope or string does not break. Let's not use that word. Direction is let's use this along string or bar or rope, kind of an inward. It really depends. So let's draw some situation here. Say we have the box, and the box is being pulled. That's too big. So we're pulling the box with this is a rope, and tension will be along the string, and this rope here, this end is going to pull the box. And since tension is towards kind of inward towards the rope itself, the tension over here is going to point this way. So I'll just draw a vector here and call this tension. So we kind of just wish the rope away and replace it with a line. This is a tension force. And we can also have a situation like this. We have a rope or a string, but there's a pulley, and there's another object. So tension at this end tends to pull inward towards the string, so it'll pull this object to the right. Tension over here will tend to pull towards the kind of inward, and that will pull this object upward. No, that's so much erase here. Okay, so let's pull this back. So let's pull this tension here upward. Right, so tension depends on the situation, and it'll always run along the string or bar, right? And the magnitude needs to be solved in situation. So what other forces could we have? We could also have some applied forces that could be in any direction. So we have some more space on the right side. Let's do friction. Okay, so friction also relies on surfaces, just as its neighbor, the normal force. So friction has two different types. One is kinetic, when objects or surfaces, to be more specific, are moving across each other. And there's also static, when the surfaces do not move across each other. So when it's kinetic, we use Fk. This is equal to mu k times normal force n, or Fn, whichever notation you like. And when it is static, we'll use Fs. The magnitude is unknown. It depends on situation. And the direction, this is basically either kinetic or static. The friction tries to reduce the relative motion between the two surfaces, or just keep the relative motion from ever happening in case of static. So reduce. Oh. Or prevent. Relative motion of surfaces. Okay, so let's draw something simple here. We'll have a box, and there's some friction here. So this mu k, this is kinetic frictional coefficient, or coefficient of friction. It describes the two surfaces in contact, how much friction they can produce against each other. So there's mu k between the surfaces, and you're pulling, trying to move the box, and gravity certainly pushes down. That requires a normal force to be pushing up, because the box would push the surface. And friction, if the motion carries out to the right, then friction points here in this direction. Okay, so think about the two surfaces. This top surface is going to move to the right, and the relative motion is they're moving apart from each other, top to the right, bottom to the left in the relative sense. So to prevent them from doing that, it should drag the top to the left, so it doesn't move as much to the right as possible. So that's an easy to figure out scenario. But there's also another scenario I can draw. So here is a truck. Okay, some load on the truck. So I'm pulling, well, the truck is accelerating away, right? So there could be a tension, something like that is being towed. Okay, so it's accelerating away, and this object, this load on the truck does not slide. So which way does the static friction point? Static friction is here because, not because things have to be static, it's because the surfaces stay static against each other. So if this car or truck is accelerating to the right, but the truck bed and the load, they're not sliding across each other, then the surfaces are static. So this thing will have to require a static friction pointing towards the left. That's okay. Let's see why. Because, well, number one, without the friction, without forces pointing to the right, the load will not accelerate to the right. It gets left behind, right? So yeah, there has to be a force to the right, toward the right. And let's imagine if there's no friction. Let's have this knob of friction turned down to 0. Then truck will accelerate, leaving its payload behind, right? So that will be a relative motion of the top surface to the right, to the left, bottom surface to the right. So to prevent top surface from going to the left, friction on the top surface must drag it toward the right. So that's why it's like this. Okay, so there's another formula that hopefully you won't get it confused with the kinetic. Is static friction has a maximum. Imagine this truck. If you accelerate too quickly, this load may slide toward the back anyway. But if you accelerate more moderately, the load will stick with the truck bed, right? So that means if you don't require large static friction, the static friction will just be enough, right? If you require a friction that's greater than the maximum static friction, there won't be any more static friction that can be supplied. So this is the maximum amount. Is mu static times normal force. So this mu static is static coefficient of friction. And normally there's a relationship, the mu static is greater than mu kinetic. The outcome of this is, say you're trying to move something, say you want to try to move a couch across carpeted room, and the couches, the legs they have dug into the carpet, so it's difficult to dislodge. So you push, you push, you push. The static friction tries to match your push, right? It tries to match your push to the maximum point when there's no more static friction that can be increased. So the couch starts to move, and once it starts to move, you better be prepared for that. Otherwise, you could fall down, because once it starts to move, the legs are no longer lodged into the carpet. It's easier to move as it starts to move. So the kinetic frictional coefficient is less than this static coefficient of friction.